All right, welcome to Computer Science 305 Programming Languages. This is our first look at Prolog. And so, Prolog is a really interesting language, if not just because it's based on logic. We're going to talk about a bunch of really basic things that make up the Prolog language system. And so, and hopefully by the time we get done, you'll have a pretty good foundation on which you can build your knowledge of Prolog. So the basic construct in Prolog is what's known as the term, right? So every Prolog is built, Prolog component is built up from terms, right? That includes all Prolog programs are themselves terms. They're completely built from these things. And all data manipulated by Prolog programs are themselves terms. So we have to understand that and keep in mind that there are three basic forms of terms, right? There are constants, which are like literal values for integers, real numbers, or they are this thing that we call atoms, and we'll talk about that shortly here. We also have variables, and then we have compound terms, which are kind of a combination of these things. So constants are pretty simple to understand. We have like integer constants like the number 123. We have real constants like such as 1.23, and then we have this concept called the atom. So an atom is similar to a symbol, or maybe more like a string constant or literal in other languages like ML and Java. But it's really just a lowercase letter followed by any number of additional letters, digits, or underscores. For example, the name Fred. Or it can be a sequence of non-alphanumeric characters like star, dot, equals, at, hash, and dollar. And then there's a special kind of atom like the empty square brackets. So bearing all this in mind, these are your basic term. So then or constant. So then we have to note that atoms are not variables, right? They look like they're a variable that we see in, for example, ML or Java, but in reality, this is not even close to what they are. We need to think of these as a symbol, a thing that is a value, and basically consider it more like a constant, a string constant from Java or ML, just without the double quotes. Variables, on the other hand, excuse me, are very similar to similarly defined as atoms, except for they start with an uppercase letter or an underscore and are followed by any number of additional letters, digits, or underscores. Note that they do not contain any special symbols, non-alphanumeric symbols. Most variables that we write will start with an uppercase letter. Those that start with an underscore or the underscore by itself are treated in a special way by the Prolog system. So keep that in mind. Compound terms, on the other hand, are an atom followed by a parenthesized comma-separated list of one or more terms. And so, as we see here, we have the atom X, and then in parentheses, the atoms Y and Z separated by commas. We also see we have plus 1, 2, and dot 1 empty square brackets. So as we can see here, it's just a very similarly, it's a very simple definition for what a compound term is. Now note that this is not a function, right? We don't really have the same type of concept as a function from ML, but do not think about this as like a function call from ML or a method call in Java. That would be a misleading. More, we should think about this as a data structure that we are constructing. And so terms have the BNF for terms in Prolog is shown here. It's pretty simplistic to understand. We just need to note that all Prolog programs and data are built from such terms, and if we understand that, we can then move along. We do note that when we are talking about operators like binary operators like plus, multiply, divide, etc., they're typically written as we see here in postfix notation, so the operator precedes a parenthesized, comma-separated list of terms. But we can also write them in infix notation, for example, 1 plus 2 rather than plus and in parentheses 1, 2. But we need to note that the infix notation is simply an abbreviation, which makes it more easily to read what's going on, rather than a new definition of this type of term. So getting all that out of the way, we can actually move into what's more important in Prolog. One of the basic constructs of how Prolog works is this concept of unification. And we're not going to get too in-depth on that in this lecture, but we will later on, I think in Prolog lecture 2. So basically, unification provides a means to do pattern matching using Prolog terms, right? So we say that two terms can unify if there is some way of binding those their variables, which then makes them identical, right? So if we add, for example, a compound term parent that has two items, right? In this case, atom, which is by itself an atom, and then child, which is a variable, and then we had a second one, which was parent, and then inside of the parentheses we had Adam and Seth. We can unify these two together by binding the variable child to the atom Seth, right? Thus making them identical. So I think we'll go a little bit more in depth on this in chapter 20, which is the second is Prolog part 2. So then Prolog programs work by collecting up a set of what we call facts and rules that describe the logical system that you're making as a part of the Prolog program. And so Prolog operates in an interpreted way, and thus the database is consistently growing in size, and then allows us to, but it gives us a place where where data is stored, and we can use to evaluate different rules that we create later on. And so the simplest thing that comes in the database is what we call a fact. It's literally just some term followed by a period. And so an example of these would be the 6 parent relationships that we see here. And so each fact, right, this is typically what facts look like. They're a compound term which defines a predicate, right? The predicate is the atom at the head of the term. And then its values are the parenthesized list of atoms, or of atoms that form that the values of that predicate, right? So this is what basically we can read these as saying is, for example, the first one would be Kim is the parent of Holly, right? That's the fact. Margaret's the parent of Kim. Herbert's the parent of Margaret, etc. So if we look at these, we can then start thinking about this as a way to start defining a family hierarchy by only having one actual predicate that gives us the way to describe this. And furthermore, we also need to realize that depending on the number of, we'll say, number of items in the parenthesized list, that gives us what we call the arity number, right? The size of that list. So this would be defining the predicate parent of arity 2. So you could have multiple versions of parent with the same arity or with different arity than any of the other definitions. So then this gets us to using the Prolog system. So I'm going to cover the using the Prolog language system, and then the second part will cover rules and then the 2 phases of Prolog. And so every two sections of this talk will be a different part of the video. So if we run Prolog, so I hope that everyone followed the actual online site and downloaded and installed SWE Prolog for their system and got up and running. And so what we want to do is we're going to work with that right now. And so I already have Atom up and running. And in my terminal, if I want to, and I've also produced the relations that we saw earlier into a relations.pl file. The extension for Prolog typically is .pl, but don't be confused. It's also similarly .pl is used by Perl programs, so you can also use .pro for Prolog, but it is associated with PL for the most part. So I would suggest using PL since we are not messing with Perl in this class. So the first thing we want to do is we want to bring Prolog up and running. So on Linux, it's SWE PL, and that brings us into Prolog interpreter. And then what we want to do is we want to consult, right? So we need to load this relations.pl file. So there's a predicate called consult, and it takes in parentheses the name of a file without the extension. But you can also apparently use it with the extension. Last time I tried it, gave me a small error. So, but anyway, the side effect of consult is that it loads up whatever it found in that file into the database and returns true if it did that. It will return false if it could not. And this is the only thing that consult's really used for. Bear that in mind. So we say consult relations, and that loads up. Oh, and we need to follow that with a period. Bear that in mind. Every line in Prolog ends with a period, just like in ML, everything ends with a semicolon. And so now we have our parent facts. So if we want to run a couple queries, we need to note that the question mark dash is the prompt for running a query. And so we can say parent Margaret Kent, and with a period, and that should return true, right? And same now. You have to understand that Prolog only understands what it knows, the facts that it has at any one time. So even though something may be true in reality, if it's not a fact that Prolog knows, it will return false if it can't figure it out. So if we were to run Fred Pebbles, asking whether or not Prolog knows that Fred is the father or a parent of Pebbles, this should return false because, as we can see up here in relations, that is not one of our actual known facts. So, but the basic concept here is that when we run a query, it will either return true or false. On the other hand, some things like consult, as I mentioned before, are only really needed for their side effects. Bear in mind, as I said before, the final period, you always have to have that. Otherwise, you will get vertical bars, basically waiting until you enter that period, because they assume that you are entering more lines than the one that you have. So it's assuming that there's more input it just doesn't know about. Okay, so if we want to continue along and actually utilize variables now, right? So it's the query is going to attempt to unify, if we give it a variable, with a fact or utilizing another rule, if one exists, to help with the unification process. And so what we can do here is we can say parent, and p is our variable, Gene. So we're asking what binding for p would make it true such that what binding for p, what value for p makes the parent predicate true when we know that the second value, the second term is Gene. And so this comes out that, as we see there in the box on the slide, that it's Herbert, and of course that is true for our system as well. On the other hand, if we say parent p Esther, right, we see that we get false. Why? Because there's nowhere inside of our database of facts that Esther appears as the second term in the list. So there's no way to unify that, and so it returns false, indicating that Prolog could not prove that query true. The interesting thing about this is that Prologs have a very flexible system and allows us to have variables pretty much anywhere in any of the positions inside of a predicate query. So we can say parent Gene, as we did before, and then of course that returns Herbert. We can say parent Esther child, and that gives us Margaret. And then finally we can have parent and then two variables, parent child. Now what this will do, right, I mean, what do we think that will do? I'd like you to think about this before I move on. And so as we can see here, well, it comes up, right? We get two values. The Kim is the parent and the child is Holly, which is, interesting enough, our first fact. And so we can assume that we're looking for any time when there's a parent and there's a child and they are not the same, and that would then indicate that that would be every single fact that is in our database right now, right? And so we could possibly have multiple values. So in order to deal with that, you can use the semicolon, which every time you press a semicolon, it will load up the next result until it hits the end, as we can see there. You can also just type a period or press enter, and that will end right there where you're at. So as we can see here, we get, after entering the semicolon, we get the same values that we expected, which is also everything that was in every fact that was in our database. Furthermore, we can also start using conjunctions, right? So if you have a list of compound terms, or just a list of terms separated by a comma, that creates in a query that the comma acts as a conjunction or an and, right? So the way we read this is we're trying to find a binding such that Margaret is the parent of some value, binding for x such that Margaret is the parent of x and x is the parent of Holly. And then this returns, assuming that we can find one, it was Kim. So if we type this out to verify that, and indeed it does return Kim. If we were to, prompting as if there might be a potential second match, so we press semicolon, and instead it comes back there is no second solution, and then it returns false. Okay, very good. Note that it will try to prove them all when you use a conjunction. The Prolog system will try to prove them all using a single set of bindings. So given that, we can start to define some more useful conjunctions, right? For example, we want to determine the grandparent relationship. So that's simply asking whether or not we have a parent, a relationship where we have some variable parent that is the parent of Kim, and we have another variable grandparent is the parent of the variable a binding for parent. So we attempt to do that, and we will find that there's a couple of solutions for this. So we say parent Kim, and parent grandparent parent, right? Looks good. That'd be yes. And so it actually asked me if I wanted to, I made a typo in that. It asked me if I wanted to correct it, so I'll do that now. We'll run that one more time. And as we can see here, it's prompting me for more input, and I give a semicolon and it gives me another solution. So it looks good. We can also develop an even deeper one to get the great-grandchild, starting from child. And so we say parent Esther child, and then we'll use another line to continue this. Parent child grandchild, and parent grandchild great-grandchild. And as we do that, it comes up with our child, grandchild, and great-grandchild, and then that's the only answer that can be proven. So it looks pretty good. All right. So this is all great. And then the next section, we'll start talking about rules that we can actually start defining in order to improve our logical system.